Assalamu alaikum students. Hopefully every one of you is fine. Today I will continue my previous lecture which was about generalized linear phase systems. In the previous lecture I defined generalized linear phase systems as h of e raised to power j omega equals a of e raised to power j omega into e raised to power minus j alpha omega plus j beta. This is the expression of generalized linear phase systems. Here this a of e raised to power j omega is bipolar function. It can be negative as well as it can be positive, whereas your phase is minus alpha omega plus beta. This expression is more generalized expression if you compare with this expression. This is a linear phase systems, but here this expression is more generalized expression for linear phase systems. So before going forward, let me first discuss its two properties. In this generalized phase expression, if the alpha, which was a delay, if its 2 alpha is a constant m and it belongs to an integer I, and if beta, which is here, if it is either 0 or pi, then the impulse response of this frequency response h of e raised to power j omega will be symmetric. That means 2 alpha minus n is equal to h of n. Then this a of e raised to power j omega will be even and real function of omega. This is even symmetry. Similarly, if 2 alpha is equal to m is integer and beta is equal to pi by 2 or 3 pi by 2, and your impulse response is even symmetric or odd symmetric around alpha, that means it must be equal to minus h of n, then this a of e raised to power j omega will be odd and real function of omega. Let me first show you how can we check the even or odd symmetry about a point for a signal. For example, you have a signal which is symmetric around point time index 2, then how can we prove it is symmetric around point 2? It is symmetric around time index 2. you have to show that this h of m minus n must be equal to h of n for even symmetric. If you want to prove that it is odd symmetric, then there will be negative sign here. So let me show you whether it is even symmetric or not. You have to prove this. Here this m is equal to 4, which is this point, and you want to show that this impulse response h of n is symmetric around m by 2 is equal to 2. You have to prove it. This impulse response is symmetric around time index 2 for m is equal to 4, which is this point. So first, for this waveform and m is equal to 4, from this h of n you can find h of n plus 4, which is time advanced version of this waveform. -4, -3, -2, -1 and 0, 1, 1 and 2. This is h of n plus 4, and in order to find that h of 4 minus n, you have to reverse this waveform. You have time reversal. You have to do time reversal for this waveform. That means you have to get this expression, which I am drawing here. If you time reverse this waveform, it will again become like this: 0, 1, 2, 3, 4. This is 4 minus n, which is equal to h of n, which is this one. Both these waveforms are same. So this impulse response is symmetric around time index 2. We will see these symmetry properties throughout the lecture today. As you know, there are two kinds of systems. One is infinite impulse response and the other is finite impulse response. You will study these systems in great details in the upcoming lectures. You can represent an IIR system as a generalized phase system, but the problem is their corresponding system function h of z will not be rational, so you will not be able to implement it. You will see in the later chapter what does it mean. Its impulse response or system function can be represented as generalized linear phase systems, but this system will not be a rational function, and in other words, if this is not a rational function, you cannot implement it. But you can easily represent your finite impulse response systems as a generalized linear phase systems. And broadly, there are 4 kinds of FIR systems that can be represented as a generalized linear phase systems based on their symmetry properties. There are 4 kinds of systems. Based on the symmetry, even or odd symmetry, or the value of m, there are 4 kinds of FIR systems. Let us discuss them one by one. The first is of type 1. In this case, 2 alpha is equal to m and it will be an even number. Moreover, your impulse response is even symmetric. It exhibits even symmetry. For example, you have a impulse response like this. One, two, three, four, and let for this impulse response your m is equal to 4, and you can easily prove, as I have just shown you, this holds this expression. This waveform satisfies this expression. It is even symmetric about m by 2 is equal to. This impulse response is symmetric around time index 2. So for this impulse response, let us find its Fourier transform. H of e raised to power j omega equals, as we are discussing FIR, its impulse response is finite. It means it is terminating at m. Here we do not have infinity here, because it is a finite impulse response system. The Fourier transform of this h of n will be 0 to m h of n into e raised to power minus j omega n. And from here, if you expand this summation, here h of 0 into e raised to power minus j omega 0 plus h of 1 into e raised to power minus j omega, here n is equal to 1. Similarly, for h of 2, e raised to power minus j 2 omega plus h of 3 into e raised to power minus j 3 omega. I am writing this term below this term because they are both equal, because due to symmetry this sample must be equal to this sample. Similarly, this sample must be equal to this sample, so I am writing this sample value here, which is h of 4 into e raised to power minus j 4 omega. This is the Fourier transform of this impulse response h of n, and here we have m is equal to 4. So from this expression, if you take e raised to power minus j 2 omega common from this expression, what you will get is you will have e raised to power minus j 2 omega. I am taking it common, and the remaining terms will be h of 0 into e raised to power plus j 2 omega plus h of 1 into e raised to power plus j omega plus h of 2 into e raised to power j 0 omega plus h of 3 into e raised to power minus j omega plus h of 4 into e raised to power minus 2 j omega. So again, due to symmetry that I have just shown you, h of 0 is equal to h of 4. Similarly, h of 1 is equal to h of 3. So I can combine these two terms and these two terms. So my expression will become h of e raised to power j omega. One question you may ask, why I take e raised to power minus j2 omega common. Here this 2 is basically your alpha, where this is the point where your waveform or impulse response is symmetric. This is the point of symmetry. That's why I took e raised to power minus j2 omega common. Now let us proceed to this expression. Here e raised to power minus j2 omega h of 0 into, I can replace this 4 with 0 because they are symmetric. Similarly, I can replace 3 from 1 here due to these properties, due to these symmetries. So I can take common h of 0 from here. What you will get is e raised to power j2 omega plus e raised to power minus j2 omega. Similarly, for h of 1, for these terms you will have e raised to power j omega plus e raised to power minus j omega, and here you have h2 into e raised to power 0. So here you can multiply and divide it by 2. Similarly, you can multiply and divide it by 2. So this is a cos 2 omega and this is cos omega. Your expression will become is equal to e raised to power minus j2 omega into 2h naught cos of 2 omega plus 2 h of 1 cos of omega plus h2. Now because your m is equal to 4 and m by 2 is equal to 2, I can replace this 2 with m by 2. Here there is a 1 here. I can replace this 1 by m by 2 minus 1. 2 minus 1 is 1. And here this 2 with m by 2. So your expression will become h of e raised to power j omega And one more thing, I can replace this 2 by m by 2 as well. So my expression will become e raised to power minus j m by 2 omega 2 into h of 0 cos of m by 2 omega plus 2 h of 1 cos of m by 2 minus 1 omega plus h of m by 2. Which can be represented as e raised to power minus j m by 2 omega summation k is equal to 0 to m by 2 ak into cos of omega k. Where ak equals 2h of m by 2 minus k for all k is equal to 1, 2, 3 m by 2 and a naught is equal to h of m by 2. So from this expression this is the expression of type 1 FIR generalized linear phase system, where this is the linear phase, here alpha is equal to m by 2 and beta is equal to 0 or pi, and this is a of e raised to power j omega, and it must be even. Actually it is even. An example of type 1 system is shown here. Here you can see this is a of e raised to power j omega it is even. Now you may ask, how is it even? It is even if you sketch it from minus pi to pi, then this part will come here and it will be even. Similarly, you can observe that this is the principal value of the phase and it is linear. It will keep going downward and it has a constant group delay, which is the property of linear phase system. So this is type 1 FIR generalized linear phase system. Now let us discuss type 2 linear phase systems. For type 2 systems, you have 2 alpha is equal to m is equal to odd number. In previous case this was even, but like previous case you still have even symmetry, which is h of n is equal to h of m minus n. You still have even symmetry in the impulse response of your system. So for such system, let's suppose your impulse response is like this. Here you have 1, 2, 3, 4 and 5. In this case you have m is equal to 5, but here m by 2 is equal to 2.5 and this is 2.5, which is your alpha. And in the previous lecture I told you if 2 alpha is the integer, then your impulse response is symmetric around alpha. So here your m is odd number, but you have still even symmetry. Using the approach that I have just used for the type 1 system, you can prove that its frequency response is equal to e raised to power minus j omega m by 2 summation k is equal to 1 to m plus 1 by 2 bk into cos of omega k minus 1 by 2 where bk equals 2 into h of m plus 1 by 2 minus k for all k is equal to 1, 2, 3 up to m plus 1 by 2. You can prove it using the symmetry present in this waveform, like I have just proved for type 1 system. So from here you can observe that here again you have linear phase, and this is your a of e raised to power j omega, and here this is alpha is equal to m by 2, and again your beta is either 0 or pi. In this case again your group delay will be equal to m by 2. Now if you observe this expression here, this term will be equal to 0 for all k belongs to integers and omega is equal to pi. That is, if you replace here this omega with pi, this cos pi times any k minus 1 by 2, this cosine function will always be 0. It means this impulse response is always 0 when your omega is at pi. In other words, in your pole 0 sketch, you have a 0 at -1. It means you cannot use type 2 FIR filter as high pass filter because its response may look like this, where at near pi it goes to 0. So it cannot be used as high pass filter, but it can be used as low pass or band pass filter. Let us see an example of type 2 FIR generalized linear phase systems. This is type 2 generalized linear phase system. This is its magnitude response. This is phase response, and again we have linear phase here. This is principal value of the phase. That's why it is between -pi to pi. Otherwise, if you plot the unwrapped phase, it will go downward. Similarly, here again your group delay is constant. Moreover, your response at pi is equal to 0. Now let us discuss type 3 system. For type 3 systems, your 2 alpha is equal to m is even number, and in this case you have odd symmetry around m by 2 in your impulse response. You have odd symmetry this time. It is also known as antisymmetric. Let's suppose you have a waveform, in this case like this one. Zero, 1, 2. Here m is equal to 2, and for m by 2 is equal to 1, here this is odd function. So using the symmetry properties, you can prove that this h of e raised to power j omega, the frequency response of this impulse response, equals j times e raised to power minus j m by 2 omega into summation k is equal to 1 to m by 2 c of k sine of omega k. Where this c of k equals 2h of m by 2 minus k, where k is equal to 1 to up to m by 2, and again here this alpha is equal to m by 2, but in this case your beta will not be 0 or pi, because you have here a j term which you can represent it as e raised to power j pi by 2, then this whole term will become j into e raised to power minus j alpha omega equals e raised to power j pi by 2 into e raised to power minus j alpha omega, and it will become e raised to power minus j alpha omega plus pi by 2. So in this case your beta is either pi by 2 or 3 pi by 2. Now here, if you observe that this sine omega k will always be 0 for all k belongs to integers, and omega is either 0 or pi. Because if omega is equal to 0 here, sine 0 is always 0. Similarly, at omega is equal to pi, no matter here you have pi, 2 pi or 3 pi up to infinity, and this sine pi k will always be 0. So you can say this type 3 system here, e raised to power j0 is equal to h of e raised to power j pi, this is pi, equal to 0. In other words, if you sketch the pole zeros of this system, you will always have zeros at plus minus 1. You will have 2 zeros here for type 3 FIR systems. So what does it represent? It represents you cannot use type 3 FIR filter as low pass or high pass filters, because its response may look like this. It must be 0 at pi and it must be 0 at 0. So its response could be like this, but you can use it as, you can use this type 3 filter as only band pass filter. You cannot use type 3 filter as low pass or high pass filters. So let us see an example of this type 3. One thing that I have left is, this is a of e raised to power j omega. It must be real valued and it must be odd function. Let us see an example of type 3 filters or system. Here the magnitude, phase and group delay are plotted for a system whose function is given as j2 sine of omega into e raised to power minus j omega. So here you can see that it is a band pass filter. Moreover, here, which is a of e raised to power j omega, this is an odd function. That is, if sine minus omega is equal to minus 2 sine omega, this is an odd function. Moreover, instead of starting phase from 0, as it was starting from 0 in type 2 and type 1 systems, here it is starting from pi by 2, because your beta in this case is pi by 2 or 3 pi by 2. This j will introduce an additional phase of pi by 2 or 3 pi by 2. So your phase is starting from pi by 2. Moreover, your group delay is constant, which is the requirement of generalized linear phase systems. So this is type 3 FIR filter. Now let us move forward towards last type, which is type 4. In type 4 systems, you have again 2 alpha is equal to m, which is an odd number. Moreover, here your impulse response exhibit anti-symmetry around m by 2. Say for example, you have an impulse response which looks like this, which is 0, it is 1, and here your m is equal to 1 and your m by 2 is equal to 1 by 2. It means this is symmetry and odd symmetry around 1 by 2. So like previous case, you can prove that its impulse response equals j e raised to power minus j omega m by 2 multiplied by summation k is equal to 1 to m plus 1 by 2 dk sine of omega k minus 1 by 2 where this dk equals 2h of m plus 1 by 2 minus k for all k is equal to 1 to up to m plus 1 by 2. I have only proved or calculated this h of e raised to power j omega of frequency response of your h of n for type 1 systems. For type 2, type 3 and type 4 systems, I am writing the frequency responses. So here again you have alpha is equal to m by 2. Your beta is either pi by 2 or 3 pi by 2 due to this j term, and this is your bipolar function, which is real and odd. Like the previous cases, if you observe this term, it will be 0 for all k belongs to integers and omega is equal to 0. That is, for omega is equal to 0, this sine 0 will be 0. But here for omega is equal to pi, this term will not be equal to 0. So you can say for type 4 systems, the impulse response, the frequency response at 0 is always 0. It means in pole 0 sketch of this type 4 system, there is a 0 present at z is equal to 1. So in other words, you cannot use it as low pass filter because you get non-zero value at omega is equal to 0 for low pass filter. This filter cannot be used as low pass filter because it is 0 at z is equal to 1. It can be used as high pass or band pass filters. Let's see an example of type 4 systems. This is type 4 system. Its frequency response is equals to h of e raised to power j omega j into 2 times sine of omega by 2 into e raised to power minus j omega by 2. So here you have omega by 2. So this is your band pass filter. Here again you have magnitude 0 at omega is equal to 0 that I have just shown you earlier. Moreover, you have linear phase as expected, but again, like type 3 case, your phase is starting at pi by 2 because your beta is either pi by 2 or 3 pi by 2, and again you are getting constant group delay. Now let us look at type 1, type 2, type 3, type 4 systems and observe the location of zeros for these systems. As you know, for an FIR system, your Z transform is like this. Here you have finite impulse response, that's why I am using here m instead of infinity, and this is h of n and z raised to power minus n. So for example, for type 1 and type 2 systems, your impulse response exhibits even symmetry. That means your h of n is equal to h of m minus n. So if you put this h of n here, what you will get is it will be n is equal to 0 to m h of m minus n z raised to power minus n. Now if you let m minus n is equal to k, then this summation will become, when n is equal to 0, your k is equal to m. Similarly, when your n is equal to m, your k is equal to 0. Whenever you have n is equal to 0, your k is equal to m, and when your n is equal to m, your k is equal to 0, and here it will become h of k, and this is minus n is equal to k minus m. Which is equal to k is equal to m to 0 h of k z raised to power k into z raised to power minus m. This is equal to h of minus z, h of z inverse. It means h of z inverse into z raised to power minus m. So for type 1 and type 2 systems, you can say your system response is equal to h of z inverse into z raised to power minus m. Similarly, for type 3 and type 4 systems, you can prove that h of z is equal to minus h of z inverse z raised to power minus m. From these two expressions, we can say that for a system for which zeros are not on unit circle, they will be in conjugate reciprocal pair form. Let us understand it with the help of a diagram. Here this is type 1, this is type 2, this is type 3, this is type 4. Here you can see this pole and this pole, and these two poles, they are not on unit circle. They have their zeros are in conjugate reciprocal form. If they are on real axis, they are reciprocal to each other. Whereas the zeros which are on unit circle, they do not have conjugate reciprocal pair. Similarly, here these are conjugate reciprocal pair. This is another conjugate reciprocal pair. This is the third one, and this is the conjugate reciprocal pair. Whereas these two poles are on unit circle, and as I have discussed earlier, for type 2 systems, you have a zero at omega is equal to pi. For type 2 systems, you cannot use it as a high pass filter. Similarly, for type 3 systems, I have mentioned that it has two zeros at omega is equal to 0 and omega is equal to pi, whereas all other zeros are in conjugate reciprocal form. And in type 4, you have a 0 at omega is equal to 0, whereas the poles which are not on unit circle, the zeros which are not on unit circle, they appear as conjugate reciprocal form. Last thing is, you can factorize any system as a combination of minimum phase system, h unit circle of z, and maximum phase system. This HUC of z is a system whose zeros are on unit circle, whereas this is the minimum phase system whose zeros are inside the unit circle, whereas this is maximum phase system whose zeros are outside the unit circle. So you can factorize any system into minimum phase, maximum phase, and unit circle systems. As you can see from here, these zeros which are outside the unit circle, they make maximum phase systems. These zeros which are inside the unit circle, they make minimum phase systems, whereas these two zeros which are on the unit circle, they are representing HUC of z. So you can express this system as the combination of maximum phase system, unit circle of z, and minimum phase system. And if you want to find the order of the system, here Mi represents the number of zeros in minimum phase system. If minimum phase system has 3 zeros, the maximum the corresponding maximum phase system must also have 3 zeros, because here you can see 1, 2, 3, 4. This minimum phase system has 3 zeros. Their corresponding conjugate reciprocal zeros are also 4 in numbers, 1, 2, 3, 4. So Mi represents the number of zeros in minimum phase system or number of zeros in maximum phase systems, whereas M0 represents the number of zeros on unit circle. So the order of the system will become 2Mi plus M0. For this system, it has Mi is equal to 2 and M0, number of zeros on unit circle are 1, 2, 3. So its order will be 2 times 2, this is Mi, plus 3 equal 7. This is 7th order FIR filter. So this is end of today's lecture, and actually it is end of chapter number 5. In the last topic, generalized linear phase systems, in the previous lecture you defined what is generalized linear phase systems, and in today's lecture you have discussed its 4 main classes. If you have any question, you can ask me directly via my email address. Thank you.